Hey guys, Ms. McCorn here. Today you are going to be looking at 6.2 and 6.3. We'll look at energy diagrams, heat transfer, and thermal equilibrium. Go ahead and pause the video, take a look at these learning objectives, and write them in your handy-dandy notebook. Okay, the first thing I want to look at is when we have a warm body, it's going to have more kinetic energy than a cooler body, which has less kinetic energy. So this is how you can look at it graphically with a lot of energy particles in, of course they're not really particles, but there's more energy when we have a warmer body. So when we look at that, when they get close together or when they're touching, we can actually transfer that energy from the body, the warmer body with more kinetic energy, into the cooler body with less kinetic energy in it. So what that's going to look like, this is going to transfer. So, as that energy is transferred, it's transferred as heat until we reach what is called thermal equilibrium. That means, and you saw that in your learning target, that means that the energy, the kinetic energy of both bodies is equal, which means that they will have the same temperature. All right, so you see here when these are in thermal contact with one another, they're going to change heat or exchange the heat or have a transfer of heat. So you see here system 1 is transferring the heat to system 2 until they reach thermal equilibrium on this side where the temperature is equal to each other. We also have the same kinetic energy in both of these systems. Okay, we also have what we call the conservation of energy here. I believe we talked about this yesterday, where energy can either be created or destroyed. And then what we can discuss now further is when we talk about work and endo and exothermic processes. If you look right here, when we have gas particles colliding, what we have right here is what we would call a piston. And a piston is something that is going to push down onto gas particles, or it can be pushed up, like in these gas particles here are pushing up on the piston. In this particular case, what we have is the gas outside of the piston is doing more work on the piston than the gas particles inside the piston here. So if that's the case, when the gas particles collide with the piston, we're exerting a force on the piston. That force is going to be work. Okay, so as the gas particles continually collide with the piston, what we can see is they're putting more pressure onto the piston. Okay? And when that happens, the pressure is going to increase as the collision rate increases, and then this is going to push down onto the system. Okay, and when we see that happen, the piston is going to go continue to move downward, and the energy is transferred from the gas to the piston, and the gas inside the cylinder here is going to contract until we reach that equilibrium of kinetic energy on the outside and the inside being equal. So the gas particles right here inside are exerting the same amount of force as the gas particles here on the outside of the piston. So what we can see happening here is when a gas system contracts at a constant temperature, we have an endothermic process. The surroundings are doing work on the system, and we talked about that yesterday with endothermic processes. So here is where we have this equilibrium where the work on the outside and the work on the inside are being constant. And remember our equation that delta E is equal to Q plus W. W is this work, and that Q is that heat transfer. So when a gaseous system contracts, what we just saw was the work on the outside of the system greater than the work from the inside of the system, so the gas contracted. This is an endothermic process. So this is what's happening. Cooling is an exothermic process. The work that we had here was an endothermic process. So then we have to actually calculate the delta E using this equation. So again, this work here on the outside of the system is endothermic, but the actual inside the system, when it cools off, that is going to be releasing heat. Now to discuss work in the exothermic process. If the pressure caused by gas particles colliding with the piston on the inside of the cylinder is greater than the outside of the cylinder, then the gas inside is doing work on the piston. So then we have energy being transferred from the gas to the piston, and that's going to be an exothermic process. So the piston is going to rise up until the kinetic energy on the outside and the inside is equal, and then it's at equilibrium. That is going to be an exothermic process. So we know that means that the system is doing work on the surroundings. So this is the system on the inside. Here's the surroundings. The piston is the surroundings. So the system is doing work on the piston, and that is what we consider an exothermic process. Now this is going to be a volume change from heating. Okay, so we know that the heating up of something is endothermic. The work being done from the inside to the piston, we know that is exothermic, but, oh my goodness, but the heating up of the inside of this here, this heating here is an endothermic process. The work being done on the piston is an exothermic process. Okay. Just to quickly look at how the calculations work, if you really want to work out the algebra yourself, you can pause the video and do that, but all of it works out to this equation here, which work equals negative P times delta V. So that's pressure times the change in the volume of the gas. So that is the equation. Again, if you want to work it out algebraic yourself, you are welcome to do that. Just a quick note, if the energy of the system, the internal energy of the system decreases, it's exothermic. If it increases, it's endothermic, or it can also remain the same during a chemical reaction. Okay, delta H, you've seen that probably all over the place. What this is it's called enthalpy, or the change in enthalpy. That's our change in what you can also say heat, or a change in energy. So when you look at that, it could be either negative or positive. So when you look at that here, when it is negative, this means it is exothermic, and when it is positive, that means it is endothermic. I paused because the pen was getting on my nerves, but when it is negative and endothermic, that means it has a release of energy. You see that pen? And here, when it is when it's negative, that's a release of energy. When it's positive here, it's endothermic. That means it needs energy for the reaction to occur. So you have to put energy into the system for that reaction. This here is called an energy diagram. You just have simple, it's arrows, and whatever energy is released, that's the same amount of energy that is put into it. So going forwards, you need negative 572. So it releases energy going forwards, but if we wanted to go back from H2O and break those bonds, you actually have to put 572 kilojoules into it. So you notice that the actual value of the number is the same, but it's negative going forwards, meaning it releases energy, and it's positive going backwards, meaning you need to put energy into it. It's the same concept here when we have a physical change with the freezing of water. Because it's an exothermic process, it's a negative value. It's the exact same number, but with a positive value when you melt water, because it's an endothermic process. Here's the energy diagram for that process. And then we have seen these energy profile diagrams before, and we know that this top of the line here is the activation energy, how much energy is needed for that reaction to occur. And we know that for exothermic, the bonds in the products contain less potential energy than the bonds of the reactants. So just quickly, in order to calculate the change in the energy, what you have to do is take the energy of the reactant and subtract the energy of the product from that. So it is reactant energy minus product energy. That is why for an exothermic reaction, it is negative, and for an endothermic reaction, it is positive. We have a touch more to do in class tomorrow. What I want to do is talk just briefly about intermolecular forces when you get into class tomorrow, and we'll do a few practice problems with that, and hopefully it'll be quite interesting. See you tomorrow.